hold the phone. Take me home. Morning coffee, vanilla latte served to go. I drink it slow. Morning coffee, cappuccino, hold the phone. Take me home. Morning coffee, vanilla latte served to go. I drink it slow. Morning coffee, cappuccino, hold the phone. Take me home. Morning coffee, vanilla latte served to go. I drink it slow. Morning coffee, cappuccino, hold the phone. Take me home. Morning coffee, vanilla latte served to go. I drink it slow. Morning coffee, cappuccino, hold the phone. Take me home.
What up, everybody? Welcome to a early morning. I don't know how early it is. For you on the West Coast, it is extremely early. For you on the East Coast, y'all are up and into your day, even though it's a glorious Saturday. Welcome to another episode of Coffee Hour with Paul. Now, this is going to be a special coffee hour because we're going to be diving into the introduction to grounding and bonding. There's a lot of resources out there for folks when it comes to grounding and bonding. And my effort with an introduction is to make sure that we set the foundation. And foundational information is so important because when somebody starts to learn the code, but they also start learning principles of basic knowledge like electrical theory and all that stuff, you can quickly get an apprentice or somebody that's new to the trade off the knowledge path pretty quickly and into the weeds. And once they're into those weeds, it's hard to get them back because people say, I heard it here, I heard it there, and all this kind of stuff. So once it's in the weeds, it's hard to get them back, right? Or once the fish go to the deep, It's going to take something very strong to get them back to the surface. So that's what we have when we're talking about fundamental basic knowledge. And that's what we're going to talk about today in grounding and bonding. Now, we'll tell you that this presentation is part of our grounding and bonding Fast Tracks Purple. And so again, if interested in that program or you want to get more in-depth understanding of grounding and bonding, then that is a great place to go to learn the fundamentals of grounding and bonding, right? So that's about the program. So it's Fast Tracks Purple if you're interested. So this is kind of based on that. And I'll give you additional information today, obviously, but that's where it's based out of, right? So that's our program. Talking about the sponsor real quick, this episode. So this episode is actually sponsored by Electrician Pride. Everybody's familiar with electricianpride.com. That is our site that supplies all of the stuff like this. Where is it right here? This shirt I'm wearing, our Electrify Electricians Only series. Bunch of good stuff over there. I'm going to be the first to tell you that some of it is a bit pricey, but it is made to order, so it is what it is. But there's a lot of good stuff over there, and I know many of you have gotten some stuff over there. Everything that we sell on that website goes straight back into our shows. Most people will know that we've got a bunch of videos coming up in the future. We have new video equipment that everything rolls back into the company. And I'm able to do that because most people know I have a day job, right? Beyond being the CEO and president of Electrical Code Academy and creating all the programs and getting our various trademarks and things like that, I also am a head of codes and standards for a large wire and cable manufacturer, Encore Wire Corporation, which pound for pound puts out as much, if not more, wire and cable than anybody, because that's all they do. We don't make boxes, we don't make tuggers, we don't make anything but wire and cable. So it's running 24/7, 365, constantly churning out product, okay? So we all have to meet a UL standard. We all have to be evaluated. So again, essentially, all wire and cable is the same. What you get from Encore Wire is probably quick access to somebody like me as a technical guy, but also, again, at the end of the day, the support is probably the key. And I can tell you, nobody will support you better than Encore Wire, okay? Our CEO, Daniel Jones, is amazing. Our VPs, our sales staff, again, very dedicated. So again, that's why I'm able to do the things I do and then take everything that we make from our company, from Electrician Pride, and put it back into the show. New cameras. I got 4 cameras. I only use one for these streams, but we have so much stuff to help make our shows better, and we got a lot of stuff coming up. So stay tuned for that. Okay, enough of that plug. All right, so today's episode is we're going to be going into the basics, introduction of grounding and bonding. So let's kind of get started in that. So I'll start and I'll take us to the introduction to grounding and bonding. Okay, so we're going to go over some principles here, and real quick, I'll answer Horatio's question. Our Fast Tracks Black program on our website is by far the best exam prep software out there. Better than, I can say this with confidence, it's better than anybody's. One, because not only does it give you the information, but it gives you access to us on Wednesday nights. And you can ask questions to me and through our app or whatever, email, anytime you have something you don't understand. Okay. Now I'm going to force you to read the material, but we're there to support you in any way. So Fast Tracks is the way to go. As Schwartzy said, and Schwartzy's always there on Wednesday nights. Absolutely. So, okay. All right. So let's get into what we've got here, and I'm going to get my presentation going, and we're going to talk about it. So bear with me while I move some stuff out of the way. All right, introduction. So what we're going to learn today in this introduction, you as a viewer, reader, if you're in our program, you're going to be able to recall the importance of using acceptable definition in terms that are applicable to grounding and bonding. Okay, so one of the biggest challenges that we have is definitions and people understanding these different terminologies, and it can get kind of wonky when it comes to grounding and bonding. Because you'll have things like grounding and it says grounded, And you need to understand the different nuances for bonding and bonded and all those type of things. So explaining and understanding terminology is extremely important. So the key ones we're going to cover. We're going to explain the importance of providing a low impedance path of proper capacity to ensure the operation of overcurrent protective device. Important to remember that you have an intentionally constructed low impedance path for ground fault current, and then you also have ground fault current paths. They're distinctly different because a low impedance path is something that you, as the electrician, you have to construct it. And you have to make sure that everything is done right to achieve that low impedance path, right? So we're going to kind of talk about that. We're going to explain the various components of the grounding and bonding system. And we're going to do this again. This is an introduction, but it is great for you that own a company. It's great for you that oversee other electricians, journeymans, apprentices, so that so you can set the foundation for that learning, right? And of course, I'm liable to go off on some sidebar topics and things like that as we move through it. But that's the basic principles. That's what we're hunting for today. We're going to summarize Ohm's law in basic electrical theory. And we're going to explain electric shock hazards and the effects of electricity on the human body. And it's different whether you're a man or a woman. It's different whether or not you have weathered and worn skin, like Schwartzy, been in the business forever, probably got hands of leather, versus somebody else that might be new, like me now, that I've got soft, petite skin. Yeah, I said it. Being out of the trade for a while kind of does make you a little soft here. But at the end of the day, you'll understand that the effects of shock on the body, and you'll understand that something as little as a 7-watt lamp in a 120 volt circuit can potentially kill you. So again, the reason that we don't typically, when we get shocked, while we don't die for the most part, is because we're not bonded right. And that's a good thing. Okay, you're wearing rubber shoes, rubber soles. You're not touching between two parts. You observe the rules of one hand behind your back, or you're very conscious and aware of how you work with electricity because you're professionals. But again, our whole concept is to make sure that we're putting something in a reasonably safe condition so that other people that are not as familiar as you and me are not going to get hurt. And that's why we do what we do in grounding and bonding. We're really protecting others. Of course, as an electrician, I want to protect us ourselves as well, right? But at the end of the day, we have to remember that what are we trying to do? We're trying to protect others as well. And so that's the whole concept, okay? Good morning, Joe. We have a CMECP in the house. Okay. All right. So what are some of the things that people talk about? What's the mystery? Grounding and bonding seems to be and I will say it's by far my favorite code panel to serve on. I serve on code making panel 5. Some of the sharpest individuals I have ever seen are in code panel 5. Now, there are a lot of sharp ones in other panels, don't get me wrong. And when I was a NEMA rep, I covered multiple panels, but I would tell you, I am so blessed to be in code panel 5 because the minds that are in that panel are just amazing, okay? Christine Porter, Phil Simmons, okay? Just the minds that are in there, just Dilip that's in there, just great, very knowledgeable minds. So Scott, our chair, just great folks. And so it's just a blessing to be in there. So I love it. You got your son singing Morning Coffee. Yeah, isn't that a catchy tune? Morning Coffee. I like it. All right. Of course, every time I play it somewhere, I get this copyright thing, even though I have bought the rights to use that, but whatever. All right, so let's look at it. So the subject of grounding and bonding of electrical system is often misunderstood. Absolutely. If I had $1 for every time somebody asked me why we have to separate grounds and neutrals downstream of a service disconnect, service equipment, I would probably be a rich man, okay? But I don't get paid for that, unless you buy my courses, of course. Related topics are often widely debated. If you go to any forum, you're going to get in arguments. I did a post on TikTok, and if you're not following me on TikTok, that is one strange little platform But again, I call it TikTok-trician. Some great electricians over there. But again, some of the stuff that I read, and I don't share all of it, mind you, because some of it is just I don't want to send. And the reason I don't share it is because I don't want to have a false narrative started in the comments. I don't want people to read them and then think that that is something that's acceptable. That's why I filter it. Okay. You can have an opinion, but if it's kind of wonky and out there, and you just keep your opinion, because I'm not going to share those type of things. And that's the same on all of my platforms. Okay. I'm just saying. All right. So are grounded systems safer than ungrounded systems? So we'll kind of look at that. People say, well, if I have an ungrounded system, or if I don't have an equipment ground run with the circuit, like those old knob and tubes, is that safer? Those type of things. So, but what we're talking about is grounded system or ungrounded systems in terms of whether it's intentionally connected to earth or not. So it's a little different. You're always, to me, going to be safer when you run an equipment grounding conductor. Even if the code allows you to use a GFCI in lieu of that for an old home, like in bathrooms or something that doesn't have an equipment ground, I always believe you will be safer with an equipment ground. But as far as the code's concerned, a GFCI puts you in a safe place. And again, sometimes that's all you can do. Article 250 contains rules that are applicable to grounding and bonding. These are generally applicable throughout the NEC, unless revised in later chapters. Remember the general rules here. Chapters 1 through 4 apply broadly all over the code. 5, 6, and 7 will modify and supplement chapters 1 through 7. So when you see things for PV in 690 and you have rules there, remember that they may supplement or modify something that's in chapter 2, which is Article 250 is in chapter 2. So kind of it's important to understand how the code works, right? So you have your general requirements, and then you have the ability to supplement or modify it, that type of thing. It says many systems. O says he follows me on Instagram. All of my social media, you should be at Master the NEC, except for Twitch, which I think is at Electrician Live. That's the only one that's different. I don't know why I didn't get at Master the NEC. I'm not sure why I didn't do that for Twitch. I'm not a gamer, so I don't do Twitch much, but I do stream on it. All right. Many systems are required to be grounded. Some are permitted to be grounded, and some are not permitted to be grounded. That's an important thing to realize in 250, that you have things that are required to be grounded. Okay, you have systems. You have some that are permitted to be, but are not required. And then you have some that are not permitted. Basically, you cannot ground it. So again, understanding those nuances, and trust me, what we're going to do is, this is just part 1 of our coffee hour dealing with grounding and bonding. So I hope you're excited, because if you subscribe to this channel, then you're going to have other episodes, because I usually, all of my stuff you have to pay for, but I made it. And I will tell you that, and I didn't tell him yet, but all of this information on these webinars that we're doing, that I'm doing for free, are all sponsored by Mr. Grunberg at Wired Up Electrical Design, LLC. Yes, sir, he's fitting the bill for all of this to make this available for all of you. So thanks, Jay. If you get a chance, give him a shout. And better yet, go listen to his podcast, the Basement King podcast. Go check that out. You can also get there by going to electricianlive.com. So Jay, thank you for sponsoring all of these webinar series with Wired Up Electrical Design, LLC, out of Colorado. All right? All right, so let's go on and get into it. All right, what other mysteries? Mystery, generally, 50 volts is the low threshold above which grounding of systems and equipment is required. Okay, that's concept. Again, in a lot of documents, they'll say that that 50 volt threshold puts you down to a point where you don't have to do things like run equipment grounds. Like, for example, a doorbell transformer. Who has ever run a equipment ground on the load side or secondary side of a doorbell transformer? Nobody. I'm just saying. All right. And regards to grounding issue, the NEC has ended that debate. There was a lot of changes to the NEC, especially Article 250 from 2005 to 2008 cycle of the NEC. A total revamping of the terminologies in 250. Totally reworked it. And it continued that effort in 2011 version. So after those dates, prior to that, it was kind of the wild, wild west. But after 2005, 2008, and into 2011, Article 250 changed. And you started getting code panel members, even there was great ones on there, don't get me wrong. But again, it's a collective minds of a bunch of people on a committee. They all started to get in sync around 2005, 2008, 2011 cycle, and they've carried it on. Of course, it's not just because I serve on those panels. I'm just saying, that's not why. All right, speaking of the same language, inconsistent use of the terms related to grounding and bonding is common. It gets happened all the time. People misunderstand different uses and terminologies. What does that do? That causes confusion. Grounded and bonded, do they mean the same thing? Are these terms interchangeable? Like an equipment grounding conductor does what? It serves a bonding function, but it also extends the connection to earth. So is it grounding or is it bonding? Yeah, it's both. And an informational note reminds you of that. But it's important that we understand terminologies, right? All right, speaking the same language, is a receptacle on the 27th floor of a building, is that still grounded? We know that it's bonded because we're running an equipment grounding conductor. But is it grounded? Dude, it's 27 floors away from terra firma, right? It's 27 floors away from Earth. Is it still grounded? Okay, well, we're going to look at that. The definition of grounded is connected, connecting to ground. So grounding is the difference between grounded. So the past tense, grounded, is the final act of you doing something. Grounding something is the action, right? Understanding definitions is essential to proper applications of the rules related to grounding and bonding, okay? Definitions, an excellent understanding of definitions is essential to grounding and bonding, obviously. Several definitions have changed since previous editions. Remember, 2005 on, it got better, and it's constantly getting better. And Code Making Panel 5 did some great work for the 2023 that's going to be coming out here in a couple months. Many rules in the NEC have become more prescriptive and less relying on the terms. Prescriptive means that the code over the time kind of tells you prescriptively what we want done. Like a prescription, everybody wants to know, what does that mean, prescriptive code? It's like taking a pill bottle and you read it and it says take one pill every hour or one pill a day. That's prescription. It's prescriptive. It's telling you what to do. So the code now is getting very prescriptive, a lot of the things with grounding and bonding, because if I tell you what to do and tell you how to do it, there's a high probability that you'll do it right, right? Okay, and real quick, before I get too far into it, do me a favor, go give me a thumbs up for these videos, okay? Appreciate it, it helps the algorithm, okay? And if you don't like it, hit the thumbs down twice. I'm just saying, all right? There's always that one guy out there, and I know who he is, that loves to hit that thumbs down, okay? I just don't know why you'd watch my videos if that bothers you. All right, let's go. All right, so let's look at some terminologies. And I'll remind you, this is all in our grounding and bonding purple series. The earth. In the code, when we're talking about it, it says the earth consists of many types of soils, depending on where you're at in the country, okay? It's all based on the electrolytes that are in the soil, okay? And dissolved salts, the different minerals, the different moisture levels, where it's drier, in some places it's extremely moist soil. All of that's going to change the resistance of the earth, okay? And we put electrodes in the earth to make that connection to the earth, okay? So soil resistance is determined largely by the consistency or the content of electrolytes that are in that soil, right? And so you could be in Arizona and it's extremely dry soil, and you could be in the East Coast, a northern East Coast, and it is constantly damp or moist. And again, your electrodes are going to have a resistance value to earth, are going to be much better where you have moisture, that type of things. Okay, so again, the earth resistance will change. So kind of keep that in your mind, that depending on where you're at, could be different. So soil resistance varies on the average from 2,370 ohms per centimeters for ash, cinder, brine, or waste, up to as much as 94,000 ohms per centimeter for gravel, sand, and stones. So you can see that the ohms are much lower in ash, cinder, brine, again, holds moisture, retains moisture. Whereas gravel drains very easily, sand drains the moisture very easily, stone, things like that, then the resistance is very high, okay? Now, because of this, obviously, we're never going to allow the earth to be a path for us to have any type of return current. It's fine for lightning, surges, high power lines on low power lines, all those type of things, right? But it is not going to be something the code allows as a return path to clear any overcurrent device. It's never going to happen, right? So let's kind of set that little nugget out there for you to chomp on first, okay? Never, ever, if you're ever in an installation or you talk to an apprentice and they'll go like, well, we'll just drive a ground rod over here because we didn't run an equipment ground. The first thing you should go is no, but should be hell no, because you can never use the earth for what we do as an electricians as a return path, ever. The resistance is too high and it's unknown. So we can't do that, all right? But we'll get into that, don't worry. All right, so the earth's ability to carry current does vary, and the utility company use it all the time, right? Why? Because they have used very high levels of voltage, and it produces currents that can clear fuses on primary sides and things like that in their system, okay? Which is totally different than what our system is, where the voltage is much lower, okay? All right, the NEC connections to earth are not permitted for the purpose of carrying current. We've established that. We've knocked that out of the way. So the term ground, again, connection to earth. What is the electrical system? Typically supplied by an electric utility, okay, transformer out of the pole, or a pad or transformer that goes down the pole to a pad where your electrician will take your underground service conductors over to the pad, okay, and that's where they make it. So anyway, supplied by the utility. But in many cases, what? We have sources that are supplied by separately derived systems. A generator, depending on how you switch the transfer, can be a separately derived system. Transformers, except for auto transformers, normal transformers stepping up or dropping down voltage, those would be separately derived systems. We have a definition of what separately derived system is in Article 100, okay? So those typically will supply electrical to the system. PV, okay, separately derived system, okay? Being careful with how that's done. If you go through the inverter, and again, their connection is made on the secondary or the primary side of the inverter to the load side. If they're connected together, then it's probably not going to be separately derived, okay? But you have to look at it and see what you have to determine it. In a generator, if the transfer switch actually switches the neutral that goes out to that generator, if it switches to neutral, then you've got a separately derived system. If it does not switch to neutral, it is not separately derived, and just think of it as a range out there or something. I'm just saying, okay? It's part of the building. It's not separately derived. Okay, we'll get into that. Don't worry. The purpose of grounding electrical systems is covered in 250.4A2, and the purpose of grounding equipment for ungrounded systems are covered in 250.4B1. So we're going to look at different pieces of that, but that is basically, we have a list of why we do grounding and when it comes to grounded systems, okay? And that is 250.4A, and we go down the list. Connecting to ground or to a conductive body that extends the ground connection. So even that equipment grounding conductor extends that connection to the 27th floor, right? It extends it. So connections to ground is accomplished by means of a recognized grounding electrode system. See Part 2 and Part 3 of Article 250, and trust me, we're going to have an upcoming episode where we talk about these different parts. So make sure you subscribe because I'm going to give that to you. We're going to talk about all the little pieces and the nuances of the grounding electrode system, okay? So again, this isn't going to be a multi-part coffee hour, all right? It's also important to understand that the link between connecting the earth to our electrical system is through our grounding electrodes. And we have 8 types of grounding electrodes that we can deal with, okay? And that'd be 250.52, gives you all the different grounding electrodes, okay? It is vital to provide an effective ground fault current path defined and described in Article 250. There's a distinct difference, folks, between an effective one, okay, an intentionally designed ground fault current path than just a ground fault current path. Now, in my Fast Tracks program, the Fast Tracks Black, which is what we use for exam preparation or to teach people the National Electrical Code in general, I have some questions that we talk about this, and I have people that will leave off the word effective, and they'll just say ground fault current path on one of the questions, and we always mark it wrong because I need you to understand that an effective ground fault current path doesn't happen accidentally. You electricians are skilled. You know what you're doing. You go through the schooling. It's all an intended thing. When we use couplings and we use the set screws or compression, when we terminate equipment grounded conductors, we do all this, it's intentional. We have to have some thought into it, okay? Now, paths that ground fault current take that aren't the effective intended path are still ground fault current paths, okay? But they're not ones that we construct. We want it to follow the paths that we construct. So, grounded objects such as metal conduits, cable with the metallic sheathing, like an MC, things like that, and structural metal may extend that earth connection, okay? So there's a lot of things that can extend that connection to earth. So let's look at this graphic here. I had somebody ask me over in TikTok if our programs have graphics. Absolutely, we have graphics, okay? And these graphics are designed by Phil, and he was who I worked with when we wrote this book. He's the primary author of this book. Phil's been around for decades. He wrote the original SOARS book for IAEI. So, I mean, he's been around the block, right? And so he uses the same graphic software that I use, which is Corel Draw, and he does really, really good graphics. So to answer that question, do we have graphics? Absolutely. In our Fast Tracks program, our graphics are done by Charles Miller, okay? Okay, and on some of my videos, the graphics are done by me, but we all use the same design software. All right, anyway, so okay, I knew somebody would ask that, or somebody sometimes does ask that. So in this case right here, so we have the connection right here. So this is a grounded system, grounded conductor intentionally connected to earth right here. Okay, on the service, you're required here to bring in the grounded neutral conductor. Here we got here. So here's our main bonding jumper right here, connecting both the. Now Phil likes to show them separate, but they could be all on one bar, and this main bonding jumper could be installed as a green screw right here on this main bar. But since you do separate them, and that's perfectly okay, this jumper right here is also the main bonding jumper that connects both the equipment ground and the grounded conductor together. So you would size this based on 250.102C1, but we're getting way ahead of ourselves at this point. All we're just trying to show you this right here. Here's your grounding electrode, whatever it may be. Ground rods, pipe plate, could be a UFR ground, could be a water pipe ground that's supplemented by another electrode. Again, it could be a ground ring, whatever it may be. You're going to size those based on 250.66, okay, right? And you're going to size that based on these conductors, by the way, on 250.66, okay? And here you can see that this goes to a transfer switch, and this one actually is switching the neutral. So this happens to be a generator, but yes, it is a separately derived system, and it has its own system bonding jumper in here, okay? Because it is treated like a separately derived system, and it has its own grounding electrodes. If you did not switch this neutral, which is probably what you get in most residential applications, if you don't switch the neutral, in other words, your neutrals go to a common bus that's solid, then this is not separately derived, and you would not put a grounding electrode out here. Now, I know I'm giving you a lot of info early that is probably not part of the introduction, but I want to make sure I clear some of these because these are questions I got over on TikTok, and I want to make sure I answer these for those viewers. Many companies like Generac, for example, require a grounding electrode. That's fine. It's just if it's not separately derived, you're not going to have this system bonding jumper, and you're just going to go from the case to the electrode to meet their rules. You're not going to connect it to the neutral. You with me? You only do that if it's a separately derived system. And it all, in this case, all depends on whether or not you're switching the neutral. Okay? So I just like to do that up front so you can see that. All right, so here's our source utility comes through. This is your main service disconnecting means. Okay? And then for 2020 code, we'll say this is outside. Okay? We'll say this is outside. We're not showing the meter because we don't choose to pay the utility at this moment. But we'll say that this meets 230.85. It's also labeled emergency disconnect and service disconnect and whatnot. Okay. All right. All right. Grounded, we're still on it. Grounded, what does grounded mean? The phrase, a conductive body that extends the earth connection is not defined, okay? So we'll see this statement in there under the term grounded or grounding. And you're gonna say, well, what does that mean? When something's grounded, or something's the past tense of that would be grounding. When somebody says that, then what they're thinking is, no, actually it's the other way. Grounded is the past tense of grounding. Grounding is meaning you're doing something. Grounded means you've done it. Either way, we're extending that connection. Well, we don't have a definition in there for the phrase, the conductive body that extends the earth connection. That's not defined. Well, a conductive element such as conduit, EMT tubing, cable, or wire that extends from the point where the earth connection is made, let's say back at the service, at one point or more grounding electrodes to another point on the electrical system where the switchboard, panel board, junction, or pull box, or a grounding receptacle or grounding type receptacle is properly connected, actually extends that earth connection. So an equipment grounding conductor extends that connection. If I have a multi-story building and I'm using the building steel, that's the I-beams, that's the structural component, okay? And I'm using that, and that's in the ground, and that's considered an electrode, but it actually runs through the building, then that's going to be a location where I can connect things like transformers to it, because that is essentially extending that connection to earth, okay? And of course, we're going to get into those details. So here's my advice. If you have those deep pressing questions on all of those things, grounding and bonding, different electrodes and all, this is your time to write them down. Get them on a sheet of paper. Bring it to upcoming episodes and ask your questions, okay? There you go. John says, I have not connected a water pipe in residential new construction in years, usually plastic. Absolutely. But if you did connect to a metal water pipe underground that qualifies 10 feet in contact with the earth, okay, then you're going to have to supplement it with another electrode. And you're not going to supplement it with another water pipe. Can't do that, right? But yes, many people aren't doing that anymore. But just remember, if it's there, you still got to connect to it, but you got to supplement it. All right, so here you go. So here you see that 27th floor extension. So here's your panel. Here's your remote distribution panel. People say, where's the main breaker? Because it doesn't have to be. It's in the same building. This is a remote distribution panel. It's protected right here on the line side, okay? So here we go right here. And the one thing to remember is your neutrals and grounds have to be separated on all remote distribution panels, okay? Whether it's in the same building or it's to a detached building, okay? So 4 conductors run out there, okay? And here you see that the actual equipment grounding conductor extends that path all the way up to the receptacle on the 27th floor. So there's your connection down through the bus, over through, down here, through that main bonding jumper, back over to the neutral, back to the source. That's what's going to allow the overcurrent protected device to clear if you have a fault down here at the receptacle point location, okay? But that is extending the connection to earth. Now, we won't get into faults and clearing faults and all that until we get into later episodes. This is, again, informational, setting the foundation. We'll get deeper into the weeds with fault current flow and how things happen as we get further in this series. All right, grounded. Extensions, what is grounded? Grounding, extension of connections to earth provided by grounding electroconductors, main bonding jumpers from neutral to equipment grounding terminal bus, like we showed in that picture. Equipment grounding conductors to panel boards, like the equipment ground that supplies the feeder. Equipment grounding conductors in branch circuits. Okay, all of that. Now, 250.4 says provides an effective ground fault current path. Okay, the effective ground fault current path is one that you, Mr. Electrician, you've created. You've made sure that you've tightened your couplings properly. You've made sure that you've made all your connections properly. You've torqued them where necessary. Okay, I know John's got his torque wrench and torque screwdriver handy, but make sure you have one. Again, people don't like to do certain things, but at the end of the day, something goes wrong, call in somebody like me. I'm going to be able to find out whether or not you torqued it or not. Trust me. Forensically, we'll find out. Okay? But in a perfect world, you're never going to have anything happen. You'll be okay. I'm just saying, protect yourself. All right. So O says I had two sources. This right here is required at the utility. This establishes a grounded conductor. This right here is your grounding electrode that's required at your service. Okay? This one right here is only connected to the cabinet through this main bonding jumper. So there's only one point of connection to the cabinet, and that's right here through this main bonding jumper. This is also the green screw that's used, but this is also a main bonding jumper because it physically ties the equipment grounds to the actual grounded conductor. Okay? With me? So essentially, this is the one point to the cabinet, and this connects to this bus through this main bonding jumper, which is sized based on 250.102C1, by the way. Okay? All right. Hopefully that answers that. All right. Grounded improperly. Equipment can be grounded and not be compliant with the NEC. So this happens a lot. A good example of this is a light pole out on a parking lot. You could have you're supposed to have an equipment ground run to it. That way it clears the branch circuit protection going to that post light. But some engineers will want you to have a ground rod at it, which is totally unnecessary, but they want it there, right? So you're not going to make that connection, okay, to any neutral. You're not. You're going to connect it to the equipment ground. You're going to make it to there. It's unnecessary. So even if you didn't run an equipment ground to a light pole, some people will still say, but isn't it grounded? Yes, because it is connected to earth at the light pole, but it's improper because you're required to run an equipment grounding conductor with the circuit, and that's what's going to clear your overcurrent device. Driving a ground rod at a light pole is never going to clear an overcurrent device, ever. Okay? So something can be grounded, but it's not done so in accordance with the NEC, which again is a safety standard. Grounding means connected or connecting to earth or to some conductive body that extends that connection to earth. So an equipment grounding conductor is extending that connection, okay? The metal framing of a building that is connected to the electrodes or might be the electrode, and we're not talking about the thin sheet metal used for studs, okay? We're talking about the structural framing of a building, okay? Big I-beams, whether they're in the earth 10 feet, those type of things, right? Or all those type of things. So again, that's what we're talking about as an extension, okay? Equipment grounding must be in compliance with an effective ground fault current path rules. Means that you have to establish that equipment grounding conductor, right? That type of, okay? Lee's doing some parking lot lighting. Remember, Lee, make sure they always run an equipment grounding conductor out there, okay? Now, I hate to say this, it doesn't always have to be of the wire type, okay? It could be the type of wiring method you're using in 250.118, but I'm a wire guy, so most people want to put that wire in there. They just feel good about it. Put it in there. All right, so here's the example we saw right here. So let's say somebody did run the circuit out there and somebody said, don't worry about it. I'll just drive ground rods at those parking lot lights. Well, that's a problem right here. It's theoretically, this parking lot light or this equipment is actually grounded, right? Because they drove a ground rod, okay? And this is permitted because this is just basically an auxiliary electrode. If you want to do it, go for it. Nothing in the code tells you the size of this conductor that goes down to it. You do whatever size you want because this would be an auxiliary type of electrode. It's not a supplemental. It's not a required. It's whatever you want if you want it. But it cannot take the place of the requirement for an equipment grounding conductor. So this would be very wrong installation. And quick math will tell you why it's wrong. If I drove this ground rod and they only have one, and let's say in a perfect world it was 25 ohms. Perfect world, okay? So if it's 25 ohms, and I'm looking there going, let's see here, 25 ohms, and you're thinking, okay, if it's 25 ohms and it's 120, okay, so it's 25 ohms, and you're thinking, well, that'll clear an overcurrent protective device. It will not clear an overcurrent protective device. We'll look at that later and I'll show you why. Because again, there's not going to be enough current that can travel through the earth, back up through the grounding, the electrode, up into the panel to actually clear this device. It's just not gonna happen. It's just not. It's impossible to take place. Okay, and we're gonna look at that in a few minutes, hopefully. All right, so there you go. Bonding. Connection to establish electrical continuity and conductivity. That's the concept of bonding, okay? When we do the act of bonding, and once it's done, it becomes bonded. The past tense, bonded, is after the act of actually doing all the things that you electricians have to do to tie everything together, okay? Tie the two pieces of metal together with a wire, they are bonded, okay? In its simplest form, the definition means the conductor and connections to connect equipment together to provide a complete path of current flow between the two metal parts, okay? Bonding ensures conductivity around suspect connections. So somebody asked me over on TikTok, would I do a video showing all the necessary needs for bonding bushings and bonding jumpers? And we actually have a video for that over on our monthly subscription program. But obviously that's going to come up in future episodes here. Okay, so we're going to be talking about it. All right, so bonded. So here's an example here. So this is one of the examples where you would need, say this is service coming in. This is the example where you would need a bonding jumper if you're encountering a eccentric or concentric KO, or you had an impairment here. Then you would need to have a bonding jumper. This also would take place in feeder applications. If you had over 250 volts to ground and you had an impaired connection, then you would need bonding jumpers. Now, there's other methods that we can do. We could remove all of the rings, and once they're all removed and do different things, but we're going to cover that in future episodes. So be excited. Make sure you subscribe and follow. All right, conduit and equipment grounding conductors of the type MC and other wire methods are permitted to be used for bonding. The armor on MC is not to be used as an equipment grounding conductor unless you have a special type of MC, like a smart ground. So Encore Wire makes smart ground, and somebody like a Southwire makes MCAP, right? Different ones, okay? Check it out. Look, Grunberg. I'm telling Grunberg he's sponsoring all this, and the man is still trying to make a buck on the affiliate program. Look at that. You know what? The dude is, he's you know. Yes, check him out. All right, so bonding with the wiring methods. So right here, here's your service coming in. Here's your service disconnect right here. We'll say that we have an impairment right here or whatever, and they're the bonding here. You need money to pay for the sponsorship of these webinars because you hadn't gotten the bill yet. I'm just saying. All right, so in this case, down here, this piece of raceway right here is bonded, okay? It's bonded through here, and in case we don't know the details, but it may or may not require a bonding jumper. If it's being used, let's say with EMT, and it's got a connector, and that makes connection to the cabinet, and those type of things, then probably wouldn't need the jumper. But the whole purpose here is to show you how everything is bonded together. Here, it's using the raceway, right? Here, since we have an MC, let's say, but you notice that there's an equipment grounding conductor running with it, right? And this is supplying the primary side of the transformer, which you're going to have to run an equipment ground to it. Don't necessarily need a neutral because you're going to derive that from the secondary side, but you do have to run an equipment ground. And here you notice in this remote distribution panel that the equipment ground is connected to the cabinet, and the cabinet's connected to this raceway. So it's all these non-current carrying metal parts are connected together right there, but you notice that the neutral is floating. It's isolated. It's not physically connected to the cabinet. That's important, okay? But as you can see, all of this is all bonded together. The act of bonding is where you do all this, you make all these connections, right? And then after that, it's considered bonded, okay? All right, bonded. Equipotential bonding is employed to equalize potential, and you're going to see equipotential bonding take place in Article 517. For healthcare facilities, you're going to see equipotential bonding take place in 547 for agricultural buildings, 555 for marinas and boatyards. 680, more notably in 680.26, you're going to see equipotential bonding requirements there. And you're going to see it in 682, which is artificial bodies of water. Those type of things. All of those talk about something called equipotential bonding, and that's keeping everything at the same potential. Because if you put metal parts and everything at the same potential, then you reduce the potential for touch hazard. Okay? So again, if you've never watched our video series on 680, it's over in our monthly subscription. It's worth the $9.99 a month for one time anyway to check that out. Go check it out. All right. Bonding conductors or jumpers. A reliable conductor to ensure the required electrical conductivity between metal parts required to be electrically connected. So bonding conductors or jumpers come in various flavors. Main bonding jumpers, they're still jumpers. Okay, we have jumpers that cross over like water meters. We'll have all kinds of different types of jumpers. But the main concept of these is what? It's a reliable conductor to ensure the required electrical conductivity between metal parts required to be electrically connected. We want it all to be tied together so they're all at the same potential. Also, for the non-current carrying metal parts, we want to make sure that they're all at the same potential, also part of the effective ground fault current path back to the source. So why? So we can clear an overcurrent device. Now, usually a wire type conductor is used to connect parts that are required to be electrically continuous. But again, it can be conduits, okay? It also can be various cable types that would do this as well, okay? Okay, equipment bonding jumpers. The connection between two or more portions of equipment grounding conductors, or of the equipment grounding conductor. So you have equipment bonding jumpers, for example, in a box that jumps over to the device, right? Or you'll have equipment bonding jumpers in panels that might jump over and bond things, okay? But you're also going to have things like supply side bonding jumpers. So and we're going to get into those in deep when we go further on. The whole concept here is to try to establish that we have different types of bonding jumpers, but their role is to tie pieces together, okay? All those type of things. So here's an example of an equipment bonding jumper. Right here, permitted to be installed inside or outside of the raceway. So here's a motor. It's coming down. And here, it's allowed to be outside. And this right here, if we're bonding, for example, this right here, this is going to be limited to not more than 6 feet. It can be inside or outside of the actual raceway, okay? If it's installed outside, then it's limited to 6 feet, okay? If it's inside, it's not going to be limited to 6 feet. Outside, it is. And if you're doing it out on poles outside, then you do have allowances in the code to be longer than 6 feet. And when we get there, we're going to talk about that in more detail. We're really just focusing on jumpers and understanding that where you can have them and what they're there for, okay? The other thing with this right here is to remember that this right here is making sure that the potential from here to here is the same, okay? They're at the same potential. And if they're close, the one other reason that we like to put equipment at the same potential if they're metal is because you could be able to touch one to the other. And the last thing we want to do is create a path that can go across the most volatile portion of our body, and that's across the heart, okay? And I'm already going to tell you up front, I'm already going to tell you that this coffee hour is probably going to be longer than an hour. So it is going to be recorded. So if you've got a bolt, feel free to leave, but I hope you stay with me. We got a lot to cover. All right, equipment bonding jumpers here where the metal conduit is metal conduit or tubing, in this case say an EMT or rigid or intermediate, serves as the bonding means. A single loose connection will impair the fault path. So all intended purposes were good. You made these up. In this case, let's say it's rigid and you're using a lock nut on each side of the connection to the box. If somebody doesn't do it correctly and we have a fault that takes place to, let's say, the box or to in this case, the raceway is, let's say, is a rigid, then what happens is the fault takes place here. Now, if there's a loose connection here, right? Loose connection right here, then remember, you're going to have current traveling here on this. And so since this box is connected to it's part of the effective ground fault current path, and now the armor, or in this case, the metal raceway is carrying current, you're basically going from a live conductor, and that is the conduit, over to the grounded component, which is the box, and across that loose connection, guess what? You're gonna read current, and you're gonna read the voltage value. And problem is that becomes a shock hazard, touch potential. And here's the funny thing. Well, I don't know, it's not so funny. I mean, I shouldn't say funny. This can sit there for quite a while and not clear an overcurrent device. So, loose connections, folks. It's so important when it tells you in the code to make things up wrench tight that you literally do it, and that you do the tight, and that you do all your set screws properly. You don't forget to do set screws. You do everything like you're supposed to, because again, we're relying on this path. And this is why a lot of engineers will specify an equipment ground in there. Not that you couldn't use the raceway. Look, I'm not here. I don't want the Steel Tubing Institute folks to jump on me. I'm not saying that. The code allows for it in 250.118, so relax if you're out there watching. What I'm saying is that a lot of engineers and designers will want you to put the wire type in there because they feel more confident that you're going to make those terminations, because that's what we're always taught. And you do have people that might get a little lax on making those lock nuts tight, or putting on a coupling properly, or the coupling could move if you don't think about expansion and contraction depending on where you install it. Maybe you're on a bridge or something and you don't follow the rules for expansion and contraction and it moves, and you could have a coupling pull loose. So at the end of the day, a lot of engineers just want the wire because they feel better about it. In fact, on a rooftop for HVAC, if you're using compression type fittings and things like that, which it's outside in a wet location, then you're required to run a wire type equipment ground in there because of vibration and movement. But again, everybody does what they want, but a lot of people, that's the reason why they put the wire type in there. So I don't have anything wrong with using the raceways and things like that. I'm just telling you why a lot of engineers and designers want the equipment ground in there, okay? So this can create a hazard. That's why, please, if you're the supervisor, make sure that you harp on your guys and gals to make proper terminations, okay? Properly secure the couplings, properly secure the connectors. Set screws have to be done, okay? That type of thing. And believe it or not, did you know that even the set screws on a coupling have to be torqued? I bet you didn't know that. There's a NEMA standard for that. They have a torque value, believe it or not. All connectors have a torque value. I know we all follow that, but they do have a value. And this is one of the reasons why, to ensure that you're going to have that effective ground fault current path. All right, main bonding jumpers. Essential for clearing overcurrent devices. Essential for allowing that current, fault current, to get back to the source, back to the transformer of the utility. Allows that current to skyrocket at the location of the fault. All of that creates that path. And without that main bonding jumper, that doesn't happen. Okay, so it's essential. So at the service, okay, it needs to be installed. Now, this could be a green screw that's supplied by the manufacturer. Could be a properly sized main bonding jumper like we saw in that image earlier, where you size the conductor properly, okay? So at the end of the day, it's vital. So that main bonding jumper, now, the main bonding jumper never takes place at a remote distribution panel. Now, you might use that screw to connect an equipment terminal bar to the cabinet, but you have to make sure that you're not making connection between the neutral to the cabinet. But at the end of the day, to call it a main bonding jumper, that takes place in the service, okay? Now, in a separately derived system, that's called a system bonding jumper. Now, essentially, it serves the same role, okay? But it's called differently, okay? So at a service, main bonding jumper is what we're doing, okay? It's permitted to be a wire, could be a bus. A lot of big switchgear probably have a bus that is that main bonding jumper, and it usually has a label on it that tells you what it is, okay? And you remove that linkage depending on how you're using that switchgear. Maybe as a remote distribution switchgear, you would remove that linkage, okay? But it's in there. And of course, a screw. And that is probably most common in your normal load centers that you would have. All right, provides a return path for fault current, completes the circuit, absolutely, in a fault condition. Many rules for main bonding jumper, and they're in 250.28. So if you ever wondered, where do I go to find the rules for main bonding jumper? What's the material it can be? Where do I need to go for sizing? Of course, it'll end up sending you to 250.102C, okay? It'll send you there eventually, right? But for sizing, the main bonding jumper and all the rules for the main bonding jumper and what you can use, and the rules that tell you it has to be a green screw if you're using a screw, has to be visible after the installation, all that kind of, that's all going to have its roots in 250.28, okay? So think main bonding jumper, think 250.28, that's your starting point, okay? All right, so here's what we've got. Here's the main bonding jumper. So here we go. Now, Phil likes to show these like this. Bear in mind that he could have brought this green wire over to this bus, and he could have put this green screw right here. But he likes to show them separately. So if the green screw was installed in this bus, and this green wire was brought to this one bus, then the green screw would be the main bonding jumper. And here, this green screw is connected to the enclosure. This is your main bonding jumper because that's what's connecting the enclosure to the grounded conductor. So you size this conductor based on the size of these conductors. You start out in 250.28, and ultimately for sizing, you're going to be in 250.102C. It's good stuff. All right. So here you see, here's your main, here's the feeders going downstream. You see the 4 conductors. Once you get down here, you see the neutral bus is isolated. And here you see the equipment ground is connected to the cabinet, right? So we have a fault right here. It gets on the non-current carrying metal parts, comes back over here. Properly sized equipment grounding conductor goes all the way back here. Current goes back through the main bonding jumper to get back to the source. It allows this fault right here. The energy skyrockets. Now, typically, you're going to have it's got to be at least 6 times the amp rating of this breaker to function. At least 6, depending on manufacturers. Trust me, it's going to be much higher than that. Okay, we're talking in the thousands, okay, of fault current. That is going to allow this breaker to trip quickly. Now, most of the breakers that we work with are what's called inverse time. That means the higher the current, the quicker they trip, right? So that sudden inrush of that massive amount of current that takes place at a ground fault is going to clear that overcurrent device very quickly. Now think about this. If you did not have this main bonding jumper allowing it to get back to the source to complete that circuit, okay, and allow that fault current to get high to clear it, what would happen? You'd have a fault here, the metal enclosure would get energized, it would come back to right here, and it would just sit right here on all these metal parts. And depending on the impedance of this equipment, of the path, of the metal and cabinets and all that, there's a great chance that you're not going to clear it. And you're certainly not going to clear it in time to protect somebody, right? So ultimately, what happens is somebody gets injured because they don't understand, all right? Now, real quickly, I'll cover why you don't want to connect this neutral to the cabinet downstream, because people ask that. First of all, that would be a violation of 250.24A5. Check that out in your code book, because that would be a neutral to case connection downstream of the service, and that would create circulating currents. So you'd have current coming back on a fault would come back on the equipment ground, and you could have it coming back on the neutral, and that means that you have all this type of connections taking place all over the place. But here's the worst condition. By intentionally connecting this neutral to the case, it means that you will always have current traveling on the neutral in this scenario. Also, it will be traveling on metal parts as well, and it causes circulating currents, and it means that you have touch hazards because those non-current carrying metal parts are not designed to carry current normally. We put them in play to carry fault current, right? So we do not want current traveling and circulating on these metal parts. That's why we have to isolate it downstream. That's the whole principle. Yes, we're going to get deeper into that as we go further into this series as well. Supply side bonding jumper. What is that? Supply side's telling you it's on the line side of the service disconnect, but it also could be on from a secondary of a transformer up to the disconnecting means. Okay, that could be the supply side because it's being supplied from the separately derived system, which is what a transformer is, right? Not all transformers. Remember, an auto transformer is not separately derived, but any other normal transformer would be separately derived. If you don't know the definition of separately derived, do me a favor. Go to Article 100. It's a great definition, but basically primary and secondary are separated by either a separator, and so they're not touching. They're in close proximity, but they're not touching. They exchange current through magnetic coupling, but your equipment grounded conductor is connected with the secondary, okay? That is intimate, but your primary and secondary is not. So they are separately, and that means that you have a whole different system that is derived from the secondary of that transformer. The same way in a generator that switches to neutral, the generator is a whole separate system from the utility because you're switching all of the connections to the utility except for the bonding parts. Okay, we want everything to be tied together and act as one because of touch potential and all that, right? Makes sense now? Okay. Also used to ensure bonding for metal enclosures for separately derived systems. We talked about that. And again, bonding jumpers are sized based on table 250.102C1 on the size of the ungrounded, that's the hot, service conductors, or when it comes to like a transformer, it's based on the size of the ungrounded conductors supplied from the separately derived system, okay? And of course, we're going to get into that as well. Now, Lee says EMT. So EMT from a secondary side of a transformer to the first piece of equipment, let's say, the EMT could be used as a supply side bonding jumper, okay? As long as it's, not flexible, that type of thing. Not used to seeing that because usually people want to use FMC to get into it. So usually it's not always EMT or it's not always a fixed type of method. And when that takes place, then you end up having to put in there and put that system supply side bonding jumper in there. Okay, so again, it depends on your installation, but very true. All right, so whoa, here we go. Got an example for that. It's almost like deja vu. All right, so here, let's say it's coming in for the service and we have some impairments here. Concentric, eccentric, or whatever, let's say coming in the top. And we can't ensure that it's actually going to be reliable. So here we've got a bonding bushing and we have a supply side bonding jumper. Again, so it makes sure that this raceway here is bonded to the grounded conductor so it doesn't get isolated, becomes a touch potential. So it's bonded together because of this impairment that we might have right here. Okay, so there you go. That's your supply side bond. Notice that it's taking place on the supply side of the service entrance conductors right here, right? And 2, that's the main bonding jumper in our example here. But here's that secondary of that transformer. This right here, this 3, that is our system bonding jumper, right? And then right here, see this coming up? That is a supply side jumper, a bonding jumper. Why is it not an equipment grounding conductor? Because equipment grounding conductors are sized based on the overcurrent device that's ahead of it. Well, there isn't any overcurrent device ahead of it here. Assuming that they met all of their secondary conductor rules, which again, there's various rules in 240.21c that say we don't need overcurrent protection at the point of tap or connection to the secondary. All right, so maybe it's a 10-foot rule, secondary conductor rule. Maybe this is part of the 25-foot secondary rule. And I have a video on that too, folks. If you don't know the secondary rules, I got them. I got videos for you. All right, so this would be a supply side bonding jumper. And you're sizing it based on these derived conductors. How about that? All right. Here's another little tip. Wherever because you're able to put the system bonding jumper at the transformer or at the first piece of equipment, just remember wherever you put that supply side bonding jumper is where you want to go to the electrodes, okay? So you don't want to put the supply side bonding jumper up here, but then down here is where you go to the electrode. If you do it up here, you want to go to the electrodes here. If you do it down here like this one's shown, then you want to go to the electrode down here, okay? All right, we're going to get deeper into that as we go further into our program. Not this one, this is introductory. All right, so the connection between the grounded circuit conductor, okay, so that's the grounded one, that's the yellow with the white coming in, okay, and the supply side bonding jumper or the equipment grounding conductor or both at the separately derived system, it is identical to the function of the main bonding jumper. It's identical concept, okay? First thing, it must be large enough so that when you do have that fault, it doesn't melt down. And incidentally, that's another reason why we have a full-sized equipment grounding conductor when we're running parallels, because you could have the fault in that one raceway, and we want to make sure it's sized enough that it doesn't melt down during the fault condition, okay? Yeah, we're going to talk about all that when we get there, all right? It's permitted to be a wire, a bus, or screw, just like the main bonding jumper, and it provides a return path for fault current, okay? So here is an example of a system bonding jumper, whether it's a transformer or whether it's a generator. Remember, it's all dependent on what? The transfer switch, right? That's key. So here we're looking at this one. So here, right here, let's look at it. So let's look at the transformer first. So it's the connection between the grounded circuit conductor. So right here, see that's the grounded conductor. And it comes down here and the connection right here. So this tells me that this right here is a separately derived system, okay, because has a system bonding jumper in it for this generator. This is the disconnect at the generator. So here it is, boom, there you go. Over here on the secondary, all right, so in this case, check this out. This one's different. Notice here that they put what? They put it all down here. So the system bonding jumper is installed at the first disconnecting means, okay? Now you notice that it runs the grounding electrode and the grounding electroconductor. Wherever we put the system bonding jumper at, that's where we want to run the grounding electrode conductor to the electrode. That's an important little tip for you folks out there, especially in commercial applications, although it applies to residential as well, okay? There you go. So this is kind of essentially allows that current at a fault to get back, complete the cycle, and what that will do will allow the tripping of the overcurrent device, just like it did in the service for a main bonding jumper. Essentially the same thing. So just think, system bonding jumper, separately derived systems. Main bonding jumper, services, okay? Solidly grounded. What does that mean? So when something is solidly grounding, it is a physical connection, right? It's connected to ground without inserting any resistor or impedance device. So if I go from my service panel and I go down to a ground rods, that connection, straight from the panel's grounded conductor terminal bus down to the electrode, that would be solidly grounded. I'm not inserting any resistor in there. I'm not inserting any impedance device in there. That is a solidly grounded connection, okay? So considered solidly grounded if a resistor or impedance device such as an inductor are not inserted in that path, okay? Makes sense? A high impedance grounded system is covered in 250.36 for those that are interested, and that would be where you put a resistor or an impedance device in there. So it's not solidly connected to earth, but it gives enough resistance in there that it kind of mimics the connection to earth. And in some systems, that's preferred. But for what most of us do, you probably are going to encounter a solidly grounded system, all right? So solidly grounded connection. So here's the good one right here. So look, solidly grounded as defined, connected to earth without inserting any resistor or impedance device. So these are just symbols for an inductor, and this is a symbol for a resistor. So this connection to earth right here, solidly grounded. So this being a delta transformer, corner grounded, this is through an inductor, and this is center tapped through, and it's between, this is the grounding electrode conductor. Then it makes connection to what? It makes connection to the resistor, okay? There you go. So these are something that has a resistor or impedance device, and this would be solidly grounded. And this is what you see the most, especially in residential, commercial, most of them. But be aware these are out there. And yes, we will touch on these in future episodes. Grounded conductor, a system or circuit conductor that is intentionally grounded. So anytime you see a conductor, it's called the grounded conductor, okay? It's not always a neutral, but it is always, if it's made intentionally connected to ground, it's always going to be considered a grounded conductor. It's a very broad term that includes both neutral conductors and grounded conductors that are not a neutral, okay? All neutral conductors are grounded, okay? But not all grounded conductors are a neutral conductor. And again, if you want to understand that, go look at the definitions of neutral conductor, and neutral point is where the neutral conductor makes a connection onto the actual system, okay? Onto the actual windings of the transformer, okay? So there you go. So again, here we've got grounded conductor because it is grounded, okay? And here, connected, this is a grounded conductor, okay, neutral. Here, grounded conductor is connected to here, which does make a connection. So again, considered a grounded conductor. Grounded conductor deleted during the process, the term grounding conductor, that actual term was actually deleted in 2011 because again, what is a grounding conductor? We have equipment grounding conductors, we have grounded conductors. There's no sense in making confusion between the two, right? So get rid of the term grounding conductor, and I usually see people using this a lot in our programs, Fast Tracks course, for example, and I'm like, please answer your question specific. It's either a grounded conductor or it's a equipment grounding conductor, okay? And it was used in chapter 8, which is a standalone chapter in the NEC. It was used improperly all the time, okay? So also for business law, we also do, and Michael says that, we have some of our courses that we will, that are part of our myceudepot.com, our partner. We have some business law classes that are available too. Reach out to me. I'll share some links with you. If you're taking a test somewhere and you need business law classes, we can link you to some of those courses. All right, equipment grounding conductor. Probably the one you encounter the most. And 250.122, when we get to that one in this series, we're going to get deep into that, whether it's parallels or whatnot. It's a conductive path that is part of the ground fault current path and I should say bonds, but it connects normally non-current metal parts of equipment together and to the system grounded conductor all the way back to the source, or to the grounding electroconductor or both, okay? So here we go. Let's look at equipment grounding conductor. In this case, it's using the wiring method. Let's say a raceway, okay? And in this case, it's using the wire. Both of which, depending on how they're listed in 250.118, both of which qualify as an equipment grounding conductor, okay? So make sure you check that out. Look at the different options you have. Again, some people don't feel comfortable with using the raceway, but the code allows it perfectly fine. And with MC, for example, you're going to have an equipment grounding conductor inside of it, okay? The conductive ground fault current path is provided by the equipment grounding conductor. Paths recognized include wire or bus, metallic raceways, and some types of like IMC, RMC, EMT, those type of things. They do provide it. Okay, and then the metal sheathing is the case with AC cable, for example. MC cable, you don't use the metal sheathing as an equipment grounding conductor unless you're doing something like a smart ground product. So that was specifically designed for that. And it doesn't get any large, you can't go past the 6-gauge conductors. So if you're using one of those smart ground products, okay? And that's where an MC actually acts like an AC cable, where you can use the armor. But that only applies on a specialty made type of MC. Not normal MC. Yes, it bonds, and the armor is used for bonding to meet that rule, but it's not for equipment grounding conductor. That's why you have the equipment grounding conductor in there, right? And normally non-current metal parts of the equipment are all tied together with equipment grounding conductors, okay? And they are not designed to normally carry current. They only do it in the case of a fault condition, okay? Ground fault condition. Now, neutral conductors carry current under normal conditions. So you're always going to have current traveling on the neutral, okay? So that's why we don't want to make those connections to any metal parts downstream of the service with that neutral, because if you give it other paths back, remember, current doesn't just travel on the path of least resistance, okay? It travels on all paths. Now, the amount of current that can travel is very dependent on the impedance of that path. Remembering that impedance is made up of three components, right? Made up of resistance, like in the wire. It's made up of capacitance, right? And inductive reactance and capacitive reactance. So all these things which are opposition to current flow, all of that make up impedance, okay? It's not as simple as a DC circuit where you really just have resistance, okay? You have this rapidly expanding and collapsing magnetic field, an AC current, and all of that can have a negative effect on current flow. So again, but we always have current traveling in the neutral. So remember, you can get just as shocked from a neutral. That's why we don't make connection to metal enclosures downstream. All right, connects together, indicated. It also performs bonding. So there, for years, many people said, well, why don't we call an equipment grounding conductor an equipment bonding conductor? Well, we have the notes that remind us that it serves a dual purpose. As you've learned by now, it serves a bonding role. It extends that connection to earth. It bonds metal parts together and also allows for the clearing of an overcurrent protected device if you size it properly. So all those things that it accomplishes, right? There's no need to change that terminology. Everybody tries, but there's no need to do that. Grounding electrodes. New definition were revised in 2008. All of the grounding electrodes that you see is in 250.52a, so check those out. We are going to cover those in future episodes. Grounding electrodes are never used to provide a fault current path. That is not why we put electrodes in. They are not to be part of a ground fault current path. That is not what they're there for, okay? They're used to make that connection to earth. One, stabilizing the voltage. Also, you could have high power lines come in contact with low power lines on the supply side, and we want to give its path to earth because utility can use the earth because of the level of the voltage they use on the primary side for the utility lines. Do a little Ohm's law, and you'll see how that works out. They do use the earth. We cannot use the earth for our applications. So all we're trying to do is establish connection, and it also stabilizes the voltage in all of our testing throughout the electrical system. That's all we're doing with it. Lightning, surges, line, high power lines to low power line, all those type of things, voltage stabilization, that's the purpose. Not for clearing any devices. Remember that concept and make sure you convey that to your apprentices and everybody else. All right, so here you go. Here's the system, here's a grounding electrode, here's a remote distribution panel in a second building. We got a feeder that's running out to it. Notice that the grounding conductor bus is isolated. And here we have our equipment grounding terminal bus right here. And this is the detached structure, right? So we have to put a grounding electrode system there, right? Now, this panel right here is also parallel back to this electrode. Why? Because through the earth, which is a very high resistive path, but we also have our equipment grounding conductor. Now, if we had a case where there's a fault here, a certain amount of current's going to travel through the earth because it is a parallel path. But the resistance is so freaking high that the majority of the current is going to travel on the low impedance path, and that is the wire. So that is going to allow it to trip that device, okay? And basically, because we provide this low impedance path, the way that the division of this current works out, that again, on the low impedance path, higher the current. On the higher impedance path, the lower the current, okay? So again, it's going to react this breaker so quickly that, but you do need to understand you do have parallel paths going on, but we're not using the earth as any current carrying path. So this makes it okay, and it's going to clear that device. And this is the only other way, there's no other way you can do it here because this detached structure is also susceptible to lightning. It's also susceptible of high power lines coming in contact with those feeders or low power line systems. Okay, you still want to stabilize the voltage. So again, all those things taken into consideration, that's why we have to establish a grounding electrode system here at the second building as well. Yes, we're going to talk about that in future episodes. A conductor used to connect the system's grounded conductor or the system to the grounding electrode or to the point of the grounding electrode system. Okay, parallel paths for neutral current is established through multiple connections to earth. Yes. All right, let's go on and get to intersystem bonding. What is this? So this definition is what you're going to have to do at your service or at a remote building where you're going to have things like communication systems there, CATV, phone systems, all those type of things, then what you need to do is you have to put in what's called intersystem bonding terminations. And you have to have at least 3 terminations. And so it's going to be either at your service, or it's going to be at the remote distribution panel that's at your detached structure, if that detached structure happens to have communication systems there, okay, like Dish Network or Direct TV or all those type of things, right? Then you're going to want to make sure that you actually establish a intersystem bonding terminations there. Now, it's required at the service. It's not necessarily required at the detached structure if you don't bring communication equipment there, if there's nothing there, okay? And theoretically, it also applies to the service location, but you're probably going to have communication systems in the building. You're going to have some kind of maybe Dish Network, or you're going to have some type of Direct TV or something like that, CATV or whatever. So for all intents and purposes, you want to make sure you make that connection there. And that is where you're going to connect those bonding components, or even the grounding electrodes or the bonding jumpers to different types of communication systems all the way back to that location, right? Okay. All right, so this is a device right here that's actually listed for use in the applications of intersystem bonding terminations. This is not listed for use in things like the connection to a CSST piping in a building, gas piping, corrugated stainless steel tubing. You have another option under the requirements in the code in 250.94, right? But this one right here, for example, is only for communication systems, because that's only thing you can bring here. You also couldn't bring things like bonding to PV systems to this type of device, okay? This is just for communication, but they do allow you to install a bus bar under another option for intersystem bonding, which you could bring communication connections for their bonding, as well as things like bonding PV or CSST and all that. They do give you more options, okay? Neutral point is if you take and I might have a picture to make this easier. So here's a neutral point. If you ever wondered what this definition is, so here's a system right here. This is the neutral point. So this is basically what you probably see at a residential. 2 hot legs and a neutral shared, okay? And here, your neutral point right there is where that neutral conductor connects, and it's 240 between them, or 120 equal to this neutral. So it's a neutral conductor. Right here, this is a Y configuration. This is the neutral point, the center point of where that neutral conductor connects. The neutral goes out to your service. So right here, this is the neutral point. This is, say, a 120, 240, 120 Y system, 120, 208. Then you would say any one of these windings connected to the neutral point from here to here, it's going to be 120. So it's the same on all of these. So this is truly a neutral conductor. It's neutral between each of the legs. Okay, so right here, we have a delta system, but we have one of the winding that's center tapped. Okay, so in this point right here, when used to derive this set of systems, okay, then this would be the neutral point. Okay, so this is a neutral conductor. All right, so you have all different types of setups. Okay, check this one out. So this one is a delta. This is a corner grounded delta. This is not a neutral conductor. Okay, because the voltages measured to this would be different. They're not all the same, okay? So again, what you measure from any of the legs to the neutral point, if they're all the same, then it is neutral amongst all of the legs, okay? So there's a difference between whether something is a neutral, but one of the distinction is these are still considered grounded conductors, okay? They are considered grounded conductors. All right, so neutral points, you see here A, there's A. That's a neutral point on a 122 40-volt single-phase system. There's B, that's the Y connected. That's a 3-phase 4-wire system. 1, 2, 3, 4, 1, 2, 3, and 4, okay? C is a neutral point on a delta connected 3-phase 4-wire system, okay? So that's a neutral point. D is a neutral point created by a zigzag grounding transformer. Okay, so this is an inserted zigzag to change voltages. That is right there, still a neutral off of this actual zigzag transformer. Okay, And then, of course, E is no neutral point because it's a corner grounded delta, so there's no neutral point, right? And this is a grounded conductor because it's connection to Earth through this termination, but it is not a neutral. Why is that important? Well, all neutral conductors are going to carry current, so they get counted as a current carrying conductor. So we need to know when a neutral conductor, for example, is considered current carrying and when it's not, and those type of things. And we learn that all the time when we're learning when we're doing conductors and when we're exceeding 3 current carrying conductors and when we have to do some kind of adjustment and things like that. It's important to understand when something's current carrying, when it's not, that type of thing. All right, neutral point, again, we kind of covered that. Separately derived systems, again, we kind of told you, said, see this one right here? So this is transformer, okay, and looking at the scenario here, number 1, right here, neutral connection right here, it's secondary of, this is utility, let's say, and here's the connection to Earth, and here's the neutral that's brought to the service, here's our main bonding jumper right here, here's our grounding electroconductor to our electrode, okay, and here's our feeder running down. Now we're feeding a transformer. There was no need in this scenario to feed a neutral to this transformer. We're required to bring it to the service. But if this transformer doesn't have a need for a neutral on the primary side, then why bring one? But you notice we still have to supply the equipment grounding conductor. Now we're deriving a neutral. Jay, stop being a salesman. Dude, calm down. Calm down, contractor. All right. So here you see secondary side, and you've got your 4 conductors. Here you see the system bonding jumper right here. Here, right here is this conductor running up. There you go. And here's your first disconnecting means. And you see that they're isolated up here. So your system bonding jumper is done out here. Everything's done out here. And you've got your supply side bonding jumper run up here. Okay. So that's kind of a layout of how the separately derived system works in this. Transformers are separately derived system except for auto transformers. Okay. Now, one of the things we want to talk about real quick is the generators that are supplied from a separately derived system in these basic fundamentals is for determining whether the system is separately derived or not. Observe how the grounded conductor is treated in the transfer switch. Okay, so basic fundamentals. I need to know whether or not it's separately derived or not. When you're dealing with generators, look at the transfer switch, right? If switched with the ungrounded and phase conductors, it said then the generator supplied system is considered separately derived. If it's not switched, then it is not separately derived. So let's look at this example here, okay? And this introduction, I should have told you, this introduction is 2-part series for the intro. So we're going to do another coffee hour and cover the second part of this introduction. So there's a lot more stuff to come, but I just wanted to give you that heads up, okay? I can't cover it all in one sitting. All right, so generator type separately derived system. And hopefully you'll join me for part 2 of this introduction. So here's your transfer switch. Notice we're switching, okay? We're switching the neutral right here. So this system is separate from this system, depending on what position this transfer switch is. If that's the case, this is a separately derived system. This has to have grounding electrodes, and you have to put in a system bonding jumper. Be very careful, because I was part of a case years ago where the equipment came with this system bonding jumper installed, but they did not switch at the transfer switch, did not switch the neutral. And what happened is you had this system bonding jumper installed and you had circulating currents on the metal parts and created a hazard and a person got hurt. Okay? So make sure you're, as an electrician, if you're installing a generator, make sure that before you connect any of the conductors going out to it, feeders going out to it, make sure that you check between the grounded point and the case and make sure it doesn't ring out. That's before you get any back feeding through these conductors. Just check it first and make sure you don't have a system bonding jumper installed if it's not separately derived. If it is separately derived and you look at that transfer switch, then you want to make sure you have a separately derived system, because if you're missing the separately derived system, I mean, you're missing the system bonding jumper, then you're not going to clear the overcurrent device, and you got a problem. Okay, very important to take those details into consideration. Fuel cells, for example, solar PV systems, they provide DC current. Remember I said something earlier, inverter and other conversion equipment create alternating current. So it goes from DC through an inverter or some other type of conversion equipment, and alternating current creating a sine wave comes out of it, right? If grounded system conductors connect directly to the inverter's neutral conductor, then it is not a separately derived system. So if you have this inverter and the connections from the DC grounding connects over and connects to the AC output, all of this connects together, guess what? It is not separately derived. Same concept. If they're not the ability to be two different systems, then it is not separately derived. And it's so important when you're establishing things to learn whether or not it's separately derived or not. Okay, so look at those connections. And I'm going to be honest with you, a good ohm meter can do that. A good continuity tester can determine whether there's that connection, but do it before anything's connected. Okay, and you guys in the PV world, you already familiar with this. You probably do this stuff all the time, making sure you're doing all that. Ground fault current path. Now, think about something. We're required to provide an effective ground fault current path so that we can clear overcurrent devices. What is it? It's a low impedance path. It facilitates what? We're going to get that breaker or fuse to blow or the breaker to trip, and we want it to remove it quickly. So inverse time circuit breakers, for example, I said it earlier, that high current allows for fast operation. That high current allows for a fast fuse to blow, right? So in order to do that, we have to make sure we construct the paths accordingly. So when we say that an effective ground fault current path, which is different, by the way, than a ground fault current path, effective means we're intentionally constructing it. We're creating that low impedance electrically conductive path designed. Our whole intent is to make up those fittings, make up those connectors, make up those terminations. Okay, all of the things that we do are done on purpose. Why? Because we want that overcurrent device, or we want to have a ground fault detector in an ungrounded system to go off. Because a ground fault in an ungrounded system will not take the system down immediately. Now, when another leg has a ground fault, then the system will clear. But an ungrounded system has a monitoring system, a detection system. There's many things like smelting plants, which have a process that might be pouring molten metal. They can't have a breaker clear right away. So they want lights to come on. They want sirens to come on. They want to let everybody in the building to go hands off. We want to put this in an electrically safe condition. So if you have something pouring molten metal, the last thing you want it to do is, as it starts to pour, have the damn breaker trip and then have it come out and spill all over people that are near it. So we want to have it continue its process and then have somebody that's trained to say, warning, warning, warning. We need to let that get to a safe position, and then we can safely shut it down. That's why people in industrial facilities, and by the way, we have a course called Industrial Wiring. Check it out. It puts equipment in a safe position. But if there's another fault to another leg in the system, then it will trip the overcurrent device, okay? So an ungrounded system is designed, and it can be safe. Okay, you still gotta have equipment grounding conductors. You still gotta have those run through the system. But we have, like in a short circuit condition, we're not gonna have it trip right away on an ungrounded system. We're gonna give us time to get it in a safe position, okay? Interesting, ungrounded systems are quite interesting. So here's an effective ground fault current path. You as an electrician, you've done all this. You're establishing all of this. You've got everything. You've got down here, you've got your equipment grounding conductor. You've connected to the enclosure. You have a fault right here. That current comes through the cabinet over to this connection here, up on the equipment ground, all the way back through the main bonding jumper, all the way back to the source, completes that low impedance path. That allows that fault current to not have a high impedance restrictive current flow. That current goes to thousands thousands of amps very quickly, blows that circuit breaker right away. That's how it all works. So you intentionally construct it. It doesn't happen by accident. That's why I'm challenging you out there now, all of you supervisors, all you leaders, all of you owners of companies. You need to hammer home the importance of, I have been to many calls where fittings are loose, okay? I've been to many calls where people don't torque things properly, okay? When it comes to an effective ground fault current path, there's probably nothing more important than making sure we clear an overcurrent device when a short circuit, ground fault, or overload condition takes place. So let's make sure that that path is intentionally constructed. It doesn't just happen. We have to follow the steps to do it right. You need to habitually train your folks on that. Properly connect all those components, whether it's the raceway, the fittings, the terminations, connection to cabinets, all of that. It carries fault current, again, to facilitate the operation of the overcurrent device, as well as, in some cases, for ungrounded systems, ground fault detectors, okay? Now, let's talk about what can make for a bad, okay, or a misconception of a poorly done effective ground fault current path. Let's look at it. Well, we have to have low impedance. So let's look at this installation right here. So this happens to be a situation where maybe the electrician, in fact, let's just say that this is an installation that was done by the basement king himself, Mr. Grunberg. And Mr. Grunberg says that equipment is hard to come by. And he's like, well, dude, I need to run an MC that has 3 ungrounded conductors, okay? So a red, a blue, and a black. And I need my grounded conductor, my white, right? Okay, but I don't have it. But I need to get that circuit there. So what Mr. Grunberg does is he runs 2 parallel MCs. And since these MCs only had black, a white, and a green in each one of them, he's like, well, it doesn't matter. I'm going to take that white because the code allows me to re-identify, right? Re-identify a grounded conductor in a cable if I'm using it as a ungrounded conductor, 200.7 C, I believe, might be C1. And so he says, I've got it covered, okay? So what does he do? He runs here. Notice what he's got. He's got one of the ungrounded conductors now in this raceway. And he's got 2 of the other ones, and he's got 2 of them in this raceway. He's got the white being redone as a red. He's got the black in here. But then he's got the blue one running in this raceway. And then, of course, what he's got a neutral here. So all of these conductors are separated, right? So 300.3b is part of 300 for those that are exam prepping out there. 300 is talking about the general rules for running the different wiring methods, okay? That's for like underground 300.5. You get all those general rules there, right? So in inductive heating and all this kind of stuff are found in 300, and that's 300.20, I believe. But by separating all of these conductors out like this, you will increase the impedance. You will increase the inductive reactance, the inductive capacitance. You will create all this, and it creates a strong opposition to current flow. You'll also create heats that'll take place, inductive heating. All of this kind of stuff that can take place depending on the type of raceways you're using, how you go through, let's say, the sidewall of an enclosure. All of those things that take place. But right here, you're also required in the code to run all of the circuit conductors together, okay? Now, you have some allowances when you're paralleling, 310.10, but in this case, this is a violation because now you've got some of the circuit conductors in this raceway, some of the circuit conductors in this raceway. They are not run together, and you're gonna have a problem, okay? And you're not gonna have an effective ground fault current path. It could be an issue, okay? Can't do this. You want to keep them all together, okay? Now, what can happen here? So, if you run them separated, all circuit conductors must be installed in close proximity. Now, I'll remind you that the code does not give you a definition, okay, of close proximity. I know. We'd like that. What is it, 1 inch away, 2 inch away? That's the same issue for bundling, by the way. When we say that when you're bundling more than 24 inches without separating, what is separation? 1/4 of an inch? 1/8 of an inch? 2 inches? tenth of an inch? Code doesn't tell you, okay? But I can tell you if they touch, then they ain't separated. I'm just saying. So at any rate, you're going to have to use your best judgment, but the closer that you can run these in close proximity, then you're going to reduce those magnetic lines of force that will cause opposition to current flow. If you keep them together, then they cancel each other out, and you have less impedance on those conductors, okay? So important, okay? Plus, again, we want to ensure a low impedance ground fault current path, so we want to make sure our equipment grounds are run, our grounded conductors are run, our ungrounded conductors are all run in close proximity, okay? All right, tested, so effective ground fault current path, tested to carry full load current indefinitely. So what we've done is anytime you have a path and it's all constructed and you're using listed components or you're using fittings that are listed for the type of wiring method you're using, if you've done all that, then it has all been tested. It's all been considered sized per the NEC and, of course, any applicable standards. EMT. So when people say, can I use EMT as an effective ground fault current path? The answer is absolutely. The Manufacturer Steel Tubing Institute, they made sure that all those manufacturers, there was testing under the Gemini project in Georgia Tech was done years ago. It provides a very good effective ground fault current path as long as your connections are done right. Okay? If you have a conductor run and you size it right, then you still have to make good connections, but you have many ways to do that. Okay? Now the NEC requires no more than 80% of rated current unless the overcurrent device is rated for 100% operation. Now, this is where you see people talk about the 125% rule and all this kind of stuff. This is kind of making reference to the fact that the typical circuit breaker, for example, is going to limit continuous loads to 80% on a circuit breaker, okay? And if you already know the rating of the circuit breaker and you want to know what the load is that would be 80% of the rating of that circuit breaker, if that circuit breaker is not rated for 100%, then you would take whatever the rating is of the circuit breaker and multiply that by what? 125%, because 125% is a reciprocal of 80. No, take that back. You take the breaker and do it at 80%. You take the wire and multiply it by 125% to find it, okay? So you do division, okay, and multiplication, depending on what you're looking for, all right? You get the point. Let's see, what else? Impedance of the fault current path must be low enough, again, or it's not going to facilitate the overcurrent protected device, okay? Hold on for a second. Yeah, somebody's texting me. All right, so hold on here. What is this here? I'm getting a text from somebody. Bear with me. I don't know who that is. So at any rate, whatever. If you got the breaker, okay, then you're going to do what? Okay, you get it. So if it was a 20 amp overcurrent device, let's do the math, 20 amp overcurrent device, and you want to find out what the current limit is of a conductor so that it's not going to, the continuous load is not going to exceed the rating of the device, 20 times 0.80, 16 amps. So if you want to check that, then you go 16 amps times 1.25, 20 amps. So multiplication either way to do it. Okay, so if I know the breaker, multiply it by 80%. If I know the wire, then I can multiply it by 125%. They're reciprocal, okay? There you go. Made that make sense there. All right. Continuous and reliable. Again, when we install an effective ground fault current path, the equipment grounding conductors, here's something you need to remember. We're not doing this temporarily. So when you make all those connections and you torque them and you do everything, remember, you're making this connection for the life of the installation. It's not expected that you're going to come back and check them, even though a lot of commercial applications, they do annual torquing and checking. The concept here is that when you do it, it's a one and done. So put that wiring system in so that you know it's done. Tighten everything, wrench tight, do what it says, make those terminations, torque it, do everything that you need to do to make sure that you're doing it right, because it's for the life of the installation. Okay? Does not carry current normally. Exactly right. Equipment grounding conductors in all the raceways are not designed to carry current under normal condition. Okay. Often a break in the path is discovered by electric shock after faulted equipment becomes energized. An improper improper neutral to case connection downstream, whereas you take a remote distribution panel and you accidentally connect the neutral to the case like you're not supposed to, you might have a system that still works because everything is connected right, and you will never know that somebody did it wrong. That's why people say, well, I don't care. I'll do whatever I want to do. We don't care about the code. You're all good until somebody gets hurt and somebody finds out that somebody did something wrong and it sat there waiting, a silent killer, until somebody comes in contact. But it's because the beautiful thing about electricity, it still works. It tries to find its path. Okay? All right. The Earth. You all know this by now. The path through the Earth is in parallel with the ground fault current return path, where there's more than one path exists, right? The Earth is not considered an effective ground fault current path. The impedance is way too high. Connections are made to Earth for purposes for, again, high to low voltage when you have for transients, when you have for high lines on low power lines, in case there's something like a car hits a pole. Lightning, get it to where it's intended to go to Earth. All of that, voltage stabilization, none of that has anything to do with what? None of that has anything to do with clearing an overcurrent device. None of it. Okay? A path only through the Earth will result in electric equipment presenting a dangerous shock hazard. Absolutely. Never ever think that you can pass through the Earth. So here's a good example. Check this out. So here is the transformer. This is a typical residential. And here you see the connection to Earth established here at the transformer. Good to go. Dropping down to the actual service equipment. Okay, very good. All right, and you have the main bonding jumper is required right here. Now the problem is there isn't one. Remember that little jumper that we put on here? Well, somebody didn't do it. They put a separate bus in there, put the screw down here, and this looks like this bus here is still floating. It's not. So here's what happens, folks. This is why it's so important. And this is why I tell people, you got that little ground screw and it's halfway sticking out in your service equipment, make sure it's screwed all the way in. I don't know how many places I've gone that I've seen it still sticking out. It's not screwed all the way in. It's so important. That main bonding jumper is so critical. Okay, so you have to have the main bonding jumper. So let's see what happens here. We have a fault downstream. Now, check this out. They didn't even run what? They didn't even run an equipment grounding conductor here. And this happens, folks. This happens. And so they did this, and people ask me all the time, you have to have an equipment grounding conductor, but they didn't. So here's what happens. A fault takes place, gets over onto the equipment. They did drive ground rods. So now it's going to try to get back to the source, okay? And there is parallel paths with the Earth, but it's such high impedance that it is still going to travel. But what happens is, because of this, it just simply creates the Earth. It acts like a load, right? It just acts like a load. And what happens is the overcurrent device will not operate. And all of these metal parts do what? They stay energized. And that's a safety concern. Look, we get the big bucks as electricians, okay? And I'm not going to say anything bad about plumbers, because I guess you could drown if you're not smart enough to wake up and get out of the house when you've got water coming in your lungs. But the reality is, electricity is always sitting there, and there's so many people. And that's what scares me about the TikTok platform. You wouldn't believe some of the stuff I read on there. It's scary. I really am. And I know you that are watching this aren't those people. But again, important. Got to have an equipment ground coming down here, okay? Important. Parallel. Okay, we're going to get into the parallels here, and then we're going to probably end this first lesson. All right? Parallel conductors. Parallel conductors installed are to be made under rules of 310.10g. Two or more conductors are connected together at each end to create a conductive path with increased capacity. So think about this. If I have 4 parallel conductors in a raceway, okay, let's just say hot conductors first. I have 4 of them. Okay, so all the reason I'm doing this is to get more capacity. One conductor has a certain amount of amperage. If I put 4 of them in parallel, I get to take that ampacity times 4. But guess what? All of these are acting together as if they're one conductor. So now the ungrounded conductor is the sum of all of these conductors' circular mill. Okay? So they have to be installed identical, the same length. Each phase, say phase A, that has to be, if it's copper, all the insulation has to be same, all have to terminate the same, all have to be the same length. And then you get to phase B, that could be aluminum, believe it or not. It all has to be the same length, same insulation type for that phase. So it's very phase specific, okay? But they all have to be the same length, okay? But I hear people all the time get it confused and say, well, if I've got 4 sets, that means an ABC in this one, ABC in this one, ABC in this one, ABC in this one. So just use phase A. That is 4 conductors. When they're connected together at each end, they act as one conductor. So you add all the circular mills up, that acts as one conductor now. That's why we're doing it in parallel. And that's the whole reason why we can get higher amps, right? That sometimes gets lost in the shuffle with people. And that's going to get real important when it comes to grounding and bonding as well. Don't worry, we'll talk about it. All right, so the concept is to have all conductors share the current equally. So that divides equally on all. And if they're all the same length, they're all the same conductor type for each phase, then again, you don't have to have all of the phases the same, just the phase you're working with. A, B, and C treated differently. And the reason is because if you're paralleling phase A, then you want to make sure that that current is going to divide evenly on all of those conductors, right? Makes sense. Otherwise, if one is shorter than the other, then what happens? Then the current's not going to be the same or distributed the same. And then for a conductor that you thought had a certain ampacity, now you might be exceeding it because it's carrying more current now than it was intended. That's the rules and why we have to parallel and make everything the same length, dealing with it, okay? All right. So this is what I'm talking about. So you see here 2 raceways. You have the black, red, blue, white, okay? This has done it. So the parallel conductors, so let's just talk about the blacks right now. They have to be the same length in either one of the raceways. They have to be of the same conductive material, copper or aluminum. They have to be in the same circular mill. So if this black is 500 kc mill, this black has to be 500 kc mill. That only makes sense, right? It has to be the same type of termination. And it says it has to be terminated in the same manner. And it has to be identical so that that current divides evenly, right? And then you go to the next set, which is the reds, same thing. Now, again, the black ones could be copper. The red one could be aluminum. I think a lot of people think you couldn't do that, but you can. Just remember that aluminum is going to have to be larger to carry the same amount of current, but you could do that. Now, the only problem that presents by mix matching with the different phases is it might mean that your raceway ends up being larger because aluminum tends to be larger. That would be a problem too, because we want to make sure that we carry those parallel consistency over to the wiring methods as well. So that's also covered under 310.10. All right. So anyway, also, if running separate raceways or cables, the raceways or cables must have the same electrical characteristics as well. So while you can use, say, phase A, copper, and phase B, aluminum, you got to make sure that the raceways are going to be the same characteristics as well, okay? And different size raceways are going to have different size characteristics of impedance. So this is why electricians get paid the big bucks. All right, so there is an allowance when you're doing underground paralleling and you have non-metallic raceways. So typically this is what we're going to do, right? We're going to put ABC and grounded conductor and the equipment ground in one raceway, and then the next one, ABC, if it's 3-phase, by the way, with the neutral and our grounded conductor, another raceway. You are allowed to isolate the phases, but it has to be under the conditions that it's an underground application and that it's non-metallic raceways. Now, why would somebody ever do this? Because a lot of times when you're using really big conductors, that when you're in a CT, for example, it allows for the lining up of the actual CT connections, because if you have to bend it or deviate the conductor, there's not enough space to do it. So a lot of times engineers will design it this way because the raceways will line up with its terminations and they don't have to change directions. That would be one example. This only works when it's underground and it's rigid non-metallic conduit, like a PVC. Only when it works. Now, when you're coming into a box, if this is a ferrous metal box with steel in it, then you're going to have to make sure that you are going to have to worry about something called inductive heating because you are separating the actual phases. So one of the ways to do that would be cut little slots between these knockouts, or you could put an actual buffer plate of aluminum or some other like brass, and that will break that magnetic chain, okay? But again, that's all in the code, and this is what we're talking about right here. So we don't want to melt down, and this would happen even with metal raceways, okay? Where you're dealing with ferrous metal raceways and they enter a metal box. You've got these conditions, but just be aware of that. And most importantly, it's going to be a condition right here because you are going to have, because of this separation, you're going to have heat and you're going to have inductive heating. And you have some options here. You can put a non-magnetic, like an aluminum plate or some type of filler plate, or you could take a hacksaw or something and cut a connection between those. And effectively what you're doing is you're creating one theoretical big opening. Yes, I know it's three separate ones, but as far as the magnetics, it treats it as one opening, and it's an easy way to get around it. Okay, so just keep that in mind if you're using that application. Now, we're going to get into this deeper in another series, but I just want you to be aware of it. Okay? All right, let's see if this is a good place to stop. I'm at slide 76 here, so we're going to stop it right there and come back to me. Well, I hope you enjoyed this first part one. I know it's a lot. I know it's high level. I know many people get this, and hopefully you'll join me for the next one where we'll go in deeper in the basics and we get further into it. We're going to talk about Ohm's law and all this type of things. So hopefully you'll check that out. When is that going to be? Well, stay tuned on my channels and you will see the notice for when that's going to take place. So hopefully you got something out of today. Again, if you have any questions, reach out to me. I'm more than happy to explain it. Until next time, folks, thanks for joining me. A little longer than the normal coffee hour. Take care. God bless.